Homework from last night was page 810. We're going to take a look at 4 questions on page 810, starting with question number 4. Number 4 says, which type of beta decay transmutates carbon-14 into nitrogen? If you remember, there's 2 types of beta decay. There's beta plus and beta minus. A beta plus particle is what we call a positron, and a beta minus particle is exactly the same thing as an electron, the electrons that we always talk about. Which type of beta particle has to transmutate carbon-14 into nitrogen? Well, I'll tell you what, the easiest way to do this one is to probably write out an equation. If we start off with carbon-14 has an atomic number of 6, by the way, and let's say we do have beta plus decay, beta positive decay. We're guessing here, right? But let's say we have beta positive. Let's balance this out. 0 plus what is 14? It's going to be 14. 1 plus what is equal to 6? 5. 5 isn't nitrogen, is it? So it can't be beta plus. Let's check beta minus just to make sure that it's that one now. 0 minus 1 beta plus what? 0 plus 14 is equal to 14. Minus 1 plus 7 is equal to 6. And if you look in your periodic table, atomic number 7 is nitrogen. So it's got to be beta negative decay. Beta negative decay that does that. Now there is one more thing that we're missing there. Anybody remember what it is? It's the squiggly thing? Sure. The anti-squiggly thing? Or the anti-neutrino? We're talking about beta negative, it's always an anti-neutrino. If we're talking about beta plus, it's always a neutrino. The squiggly thing or the anti-squiggly thing, as Matt likes to say. And we've just written out the process for this decay already. Next question, number 6. Explain why the daughter nucleus in an alpha decay often emits gamma radiation. The daughter nucleus. The daughter nucleus is like the product, right? So we have, in chemistry, we have reactants and products. In nuclear physics, we have parent and daughter. So the parent nucleus is what we start with, the reactant. The daughter nucleus is what we end with. That's the product. Why does the daughter nucleus in an alpha decay often emit gamma ray? Well, if you remember that, you remember how all of these types of radiation are produced. Alpha was produced when we have too many protons. Remember those 2 forces in the nucleus that we looked at? The attractive, strong nuclear force, and the repulsive electrostatic force. Okay? Yeah. If the attractive force is bigger than the repulsive force, the nucleus stays together. If the repulsive force is bigger, then it breaks apart. So alpha decay occurs when you have too many protons and therefore too big of a repulsive force. Beta negative occurs when you have too many neutrons. Now it's not a force thing when we have too many neutrons, it's an energy thing. When you have too many neutrons, it's energetically unstable. Energetically unstable. And when it's energetically unstable, something has to happen. So it changes a neutron into a proton, and that in the process gives off an electron so that we don't violate the law of conservation of charge. You have too many protons. Well, sometimes the force of repulsion is too big. Sometimes the energy isn't quite right, and you change a proton into a neutron and a positron. And the positron leaves, the neutron stays behind. Finally, gamma decay occurs as a byproduct of one of the ones that we just talked about. If you have, let's say, alpha decay occurring, then what happens? The nucleus is left in an excited state, but it doesn't want to be there. So it goes back down to its normal state by giving off energy. And the energy that it gives off is a gamma ray. So why does the daughter nucleus in alpha decay often emit gamma rays? Because after alpha decay, the nucleus is left excited, doesn't want to be there, so it goes back down to its normal state, giving off energy or a gamma ray in the process. Question number 9. Explain whether the atomic number can increase during nuclear decay and support your answer with an example. Can the atomic number increase? Sure it can. Sure it can. By what mechanism can the atomic number increase? If you have alpha decay, the atomic number goes down by 2. If you have beta positive decay, the atomic number goes down by 1. If you have beta negative decay, the atomic number goes up by 1. For instance, if we have carbon-14 undergoing beta negative decay, we end up with 0, 14 on the right side, minus 1 and 7 on the right side. That's nitrogen, plus an anti-neutrino. But you notice here in that process that the atomic number went from 6 to 7. So during beta negative decay, the atomic number goes up. During beta positive or alpha decay, the atomic number goes down. And finally, number 12. Number 12 says, in a process called electron capture, a nucleus absorbs an electron and emits a neutrino. This is new, electron capture. We've never seen that before. How could we possibly be expected to answer a question that we've never talked about before? Well, I've promised you this before, and I'll promise you this again right up until the moment you go into your diploma exam. Everything you need to know, I will have taught you. I promise. Everything you need to know, I will have taught you. I guarantee it. Now, haven't I already lied about that if we're talking about electron capture here and I haven't talked about electron capture? No. I've taught you what you need to know about this question. So what, we haven't talked about electron capture. What do you got to do? You got to balance equations, right? You got to write a nuclear equation. You know how to do that. We've taught you how to do that. In a process called electron capture, a nucleus absorbs an electron. Let's say our nucleus is carbon-14. Honestly, I'm not sure if carbon-14 would capture an electron or not, but let's say that it does. Okay? If it does, our electron is going to be on the left-hand side, not on the right-hand side. It's not beta negative decay. We're not producing an electron. We're absorbing an electron or capturing an electron. So it's going to be carbon-14 or whatever element plus the electron goes to whatever. Well, 0 plus 14 is 14, minus 1 plus 6 is 7. It's 5. We'll look at our periodic table. We see what atomic number 5 is. And it is boron. There you go. What effect does electron capture have on the atomic number? Well, the atomic number went from 6 to 5. When you release an electron, the atomic number goes up. But when you absorb an electron, the atomic number goes down. Let's write a general form of this, actually. We've got X, element X with an atomic number of Z and a mass number of A. We absorb an electron, and it goes to A, and then Z minus 1 times whatever element it is. We'll call it element Y. There's the general form of it. Now we want to compare electron capture with beta decay. Well, in electron capture, you're absorbing an electron rather than releasing an electron. There's one way of comparing it. Absorbing versus releasing. The second way of comparing it is this. The atomic number in electron capture goes down versus the atomic number in electron emission or beta negative decay. The atomic number goes up. Right? We go from, if it's electron capture, we go from 6 to 5. If it's beta emission, then we go from 6 to 7. And the third thing that I thought of there, talking about electron capture versus beta decay. In electron capture, what's going on here? What's the mechanism that allows this to happen? We have 6 protons going to 5 protons. We have a proton that's being changed into a neutron. But how does that happen? It's the electron and the proton that end up producing the neutron, right? The electron that we have right here in one of these protons that ends up giving us a neutron versus beta decay, where in which case you have a neutron produces a proton and an electron. So it's the opposite, right? Electron capture is exactly the opposite of beta emission. Make sense? You're going to have to answer a question about electron capture on your exam? I don't know. It's not a curriculum objective in Physics 30. I can tell you that what I can tell you with certainty is they're not going to say something about electron capture without giving you information like this. They're not going to expect you to know what electron capture is without explaining it. But just like anything else, they could give you something new and explain it. Okay. Bottom line is, if you see something like that, don't panic about it. You know what to do. Okay? Treat it like something we know, like balance the equation like we did in beta decay or alpha decay or whatever the case may be. I want to define a new term now to take us to the next level, the next step in radioactive decay. The term's called half-life. If you take Math 30, or have taken Math 30, which I guess all of you, most of you would have at this point, you might know a little bit about half-life already, because you would have done exponential growth and exponential decay, and probably one or two of your examples would have involved something called half-life. We're going to define half-life is the time that it takes 1/2 of a radioactive sample to decay. So let's say that we've got carbon-14. We know that carbon-14 undergoes beta decay by this equation. After one half-life, we're only going to have half of the carbon-14 left. So in other words, after one half-life, if we start with a kilogram of carbon-14, then we're going to have only 500 grams of carbon-14 left. Now, that doesn't mean it's gone, because we still have nitrogen-14, right? We still have a kilogram of stuff. It's just that we have only 500 grams of carbon-14. And after one more half-life, we've got 250 grams of carbon-14. And after one more half-life, we've got 125 grams of carbon-14, and so on and so on and so on. We keep going down by a half with each half-life we have. Now, what I sometimes like to do is add a word to the definition that you have in your notes already. The word statistically. The time that it takes statistically for 1/2 of a radioactive sample to decay. Why do I add the word statistically in there sometimes? Well, because this is a natural process. This is a random process. We can predict what's going to happen and how quickly this this radioactive nucleus is going to decay, but it's only a prediction based on probabilities. It's only a prediction based on what's happened in the past. We don't know for sure how quickly it's going to decay because we can't control it. It happens when it wants to happen. Let me give you an analogy to maybe help you understand that. If I've got coins, let's say I've got two coins. They're both on heads. Let's say heads means not decayed. Tails means it's decayed. So it's radioactive if it says heads, and it's not radioactive if it says tails. Let's say the half-life, which by the way we're going to give the symbol T1/2 to, the half-life is 3 minutes. That means I'm going to flip both of these coins in 3 minutes. Now, I got a lot of extra time here. That's okay. Okay, it takes 3 minutes for me to flip these two coins. After one half-life, or after 3 minutes, how many radioactive nuclei am I going to have left? How many heads am I going to have left after 3 minutes? Statistically, I'm going to have, after 3 minutes, one head and one tail, right? So I'm going to have one nucleus left that's still radioactive, that is. In the real world, does it end up being one heads and one tails? Sometimes. Sometimes not, right? If we're dealing with a small sample size, really all bets are off. Statistically, it's still half of a sample decaying after 3 minutes, but a small sample size like 2 nuclei, we don't really know what's going to happen. The predictions that we're going to make are going to be based on A, observations that have been made previous, and B, making the assumption that we have big enough sample sizes. So for instance, instead of having 2 heads to start off, we have 1,000. We flip them all in 3 minutes. How many heads are we going to end up with after 3 minutes? About 500. Could it be 497? Sure it could. Could it be 503, 508? Sure it could. But it's going to be pretty darn close to 50%, right? When we have a bigger sample size, okay, the assumptions that we make are a lot safer. Does that make sense? You get 2 nuclei, maybe after one half-life, they both decay. Or maybe only half of it decays. But if you have 1,000, it's pretty safe to say that about 50% will decay after one half-life. The only way we really know is after the fact. Count them after the fact. We make predictions, but we can never be sure until after the fact. Now understand, I'm telling you this isn't a simplification. I'm not telling you this because, oh, you're physics 30s, you're not smart enough yet to understand what's really happening. Nobody can predict any better than we're going to predict here. It's a natural random process. Nobody can control it any more than you can't predict with any more certainty, nor can anybody else predict with any more certainty that you're going to have 500 nuclei left after one half-life, any more than you can that you'll have 500 heads left after flipping 1,000 coins. Okay? Odds are, but you never really know for sure. So the half-life is the time that it takes statistically for half of it to decay, and the symbol is T1 half. Now, here's an equation. N stands for the number of half-lives. It's going to be equal to T over T1 half. What do you think T stands for? The number of anything is the total divided by the amount for one, right? The number of half-lives is the total time divided by the time for one half-life. This is not on our data sheet. You're going to have to remember this one or figure it out. The number of half-lives that have elapsed is the total time divided by the half-life. If the half-life was 3 minutes and 21 minutes have gone by, then that means 7 half-lives have elapsed. 21 divided by 3 is 7. If the half-life is 5,700 years, if 11,400 years have gone by, then N is equal to 2. 2 half-lives have elapsed. One more equation that you might recognize from Math 30. This one is on your data sheet. How many people recognize that? N is equal to N times 1/2 to the little n, yeah? You recognize any other forms of it too? Where have you seen this before? Talk about exponential decay. Did you do exponential growth in math class? Compound interest? What would be the difference? What would be the difference? How could we modify this equation to make it growth as opposed to decay? This wouldn't be a half, right? This would be a different number. If you're growing, this number is bigger than 1. If you're decaying, this number is smaller than 1. The good news is in physics 30, all we're talking about is decay, and it's specifically radioactive decay, where after each half-life, half of it decays into what we started with. All right, N stands for the amount that we finish with, the final amount, we'll call it. N sub 0 stands for the initial amount, the amount that we start with. And of course, little n is the number of half-lives. This doesn't have any units because it's just a number. This has units. Could be grams, could be kilograms, could be moles, could be just a number, could be a percent. It could be, here's a new unit, a becquerel, which stands for how many decays per second is taking place. Don't lose any sleep over that unit, okay? Really, don't. It can be any unit you want as long as it indicates an amount and as long as these units for the initial amount are the same. If you see a unit in the context of radioactive decay and you don't recognize that unit, it's going to be some unit of decay. Make it N or N0 because it's going to be an amount. All right, there's my 2 equations. How many of you have gone through Math 30? Probably almost all of you? No? Okay. That's okay, because in the end, what I'm going to show you, 2 examples here. One of them doesn't make any difference at all whether you've gone through Math 30. The second one I'm going to show you is going to use a mathematical technique that you probably haven't learned if you haven't gone through Math 30, but there is a backup plan for it as well to make it a little bit easier. You probably pick it up pretty quickly anyways. Here's the first question. It says radon-222 has a half-life of 3.82 days. What percent remains after 2 weeks? Well, I'm going to say the number of half-lives is T over T1 half. T is, I'm going to say 14 days. How come I went to days there instead of weeks? I could have went to weeks. I could have left it as weeks, right? 2 weeks. But I would have had to convert the half-life to weeks. And I think it's easier to convert 2 weeks to days than it is to convert 3.82 days to weeks. We divide those 2 numbers, and when we do, we end up getting 3.6649. That's the number of half-lives that have elapsed. How much remains after 2 weeks? Well, we want to find the final amount. So we're going to say n is equal to n sub 0, 1/2 to the little m. If you've taken Math 30, you've probably done a question or two like this, eh? Radioactive decay? Everybody remember that? It's a perfect example to give in math class, right, when you're talking about exponential decay. What's n0 going to be? How much do we start with? We're not told, are we? Where are we? How much do we start with? If we end with a certain percent of what we started with, how much do we start with? When you're dealing with a percent, the initial amount is almost always going to be 100%. We started with 100%. Let's pull out the calculator and do this one as a group now. Let's say 100 times 0.5, and let's just use this little button right here, the hat button, 3.6649. We do the math there, we get 7.88%. We started with 100%. After 2 weeks, we end up with 7.88% of what we started with. Are we sure about that? No. If we're predicting this ahead of time, maybe it ends up being 8%. Maybe it ends up being 7.4%. But if the sample size is big enough, if we had enough radioactive material, then odds are we're going to be pretty darn close. But you know what? We can't do any better. No matter how good we get and how smart we get, we can't do any better until after the fact. After the fact, we can measure how much we have, but as a prediction, it's the best we can do. I got one more example for you that's printed in the notes that I photocopied for you. It says the half-life of carbon-14 is 5,730 years. By the way, half-lives will vary depending upon what element you've got, from less than a second for half of it to decay to thousands of years for half of it to decay. Carbon-14, half of it will decay in about 5,700 years, give or take. How long does it take 12.5 kilograms to decay to 400 grams? All right, I'm going to say T1 half. I'm going to write down some givens for this one. T1 half is 5,730 years. By the way, if you ever see this, an A after it, what does that mean? 5,730A means the same as 5,730 years. It's Latin, annum, right? The Latin for year, annum. So be prepared for both of those. 5,730 years, 5,730 annum, it's the same thing. We're looking for T here. We've got N is 400, we'll say 0.4 kilograms. And we'll say N0, the amount that we start with here, is 12.5 kilograms. We want to find T. The only equation that has T in it is the one that's not on our data sheet. Let's rearrange that, N times T1 half. The only problem is I don't know what N is. All right, that's no big deal. We'll go to my other equation here now. N is equal to N sub 0, 1/2 to the little n. Got N0, just solving for a little n, right? How do we do that? How do we solve for a little n here? Anyone? Who takes Math 30 right now? Nobody? You guys have a math diploma exam coming up in less than a month, eh? How would you solve for a little n? Yeah, there's a couple ways you can do it. One way is using logarithms, and you probably don't recognize that. You probably never heard of that, logarithms. Oh, have you? Okay, you probably did actually in chemistry a little bit. But don't worry, there's a backup for it. And some people even that have used logarithms will use the backup because they don't like logarithms. We're going to do it both ways here. To solve for little n using logarithms, we're going to say little n is equal to log n over n sub 0 over log of 1/2. So it becomes log 0.4 over 12.5 over log of 0.5. Let's do that on our calculator now. The log button, brackets, 0.4 over 12.5. Press enter. Let's divide that by log 0.5. I end up with 4.97. Little n is 4.97. So if I take that number, 4.97, and multiply it by the number of half-lives, multiply it by the half-life of 5,730 years, we end up getting a total time here of 28,453 years. 2.85 times 10 to the 4 years. 28,000 years have gone by before I'm down to 400 grams. What's the other way of doing this? It's what I call the divide by 2 method. Make a little table. The first column of the table is going to be little n, the second column is going to be big N. Well, little n is a number of half-lives. After 0 half-lives, how much do I got? It's what I started with, 12.5 kilograms. After 1 half-life, how much am I going to have? Statistically, at least. Okay, we know that it doesn't have to be exactly this number, but it's the best we can predict. We're going to have 6.25 kilograms left. After 2 half-lives, we're going to have 3.125 left. After 3 half-lives, we keep dividing by 2, right? 3.125 divided by 2 is 1.5625. After 4 half-lives, keep dividing by 2, 0.78125. After 5 half-lives, keep dividing by 2, 0.391. All right, I need to get down to 0.4. I'm pretty much there. So it looks like little n is going to be almost 5. Here's what the curriculum objective says that you have to be able to do with this. It says you have to be able to perform simple, non-logarithmic half-life calculations. In other words, could you get a question like this? Yes, you could, where you're allowed to use logarithms. But there has to be another way to do it. In other words, if you get a question like this, little n either has to be a whole number or so close to a whole number that it might as well be a whole number. You won't get a little n, you will never get a little n that's 4.45, unless you're using this equation, right? Okay, then it might be 4.45. But you'll never get little n from here that's not either a whole number or really, really close to a whole number. Now, if you multiply 5 by 5730, your answer might be slightly different. Okay, both would be accepted because they're going to expect you to keep dividing by 2 and then say, oh, 4.97, that's like 5. Or to use logarithms and get the other slightly different answer. Okay, both would be accepted because both are acceptable methods. All right, we just did 2 examples. Your homework is page 814, questions number 1 and 2, homework for tomorrow.